All right, this brings us to the second Test of Time award that we are honoring here today. This award goes to the paper Wake on Wireless, an event-driven energy-saving strategy for battery-operated devices from MobiCom 2002. The paper is authored by Eugene Shi, Victor Ball, and Michael Sinclair. And the Test of Time committee found that this paper pioneered the systematic use of low and high power radios to improve battery consumption in energy constrained devices, and by separating the data and control channels to achieve that. This approach is now frequently used in mobile devices that we use daily. It also contributed an experimental methodology that has been followed and built on in many papers after that. And just recently, you might have seen the 802.11 BA standard incorporating some of these ideas that were pioneered many years ago in our community. Please welcome up Victor Ball. He's no stranger to this community, as you know. Congratulations.
Well, first of all, thank you very much. I'm actually really happy that Mike is here with me. Mike is the co-author, and we'll get him up here in the stage after I finish what I have to say. I did not plan to give any slides, but Jeetu last night said, oh, Victor, the other Victor, is actually working on these slides. And I'm like, oh, really? But we don't really do slides. But he says, oh, I should tell him. But then I go to my room and I said, shucks, I should actually do some slides. so we developed this thing. So I do have some slides now. So anyway, without further ado, you guys are really serious, so we need to actually, I guess, move along. All right, so this was done, this paper, I'm so sorry, it doesn't show very well, I guess. That's too bad. This paper was done in 2002, so that's 16 years ago. What I'm going to do is because it's not showing too well, I'm going to just rush it, and you'll probably just see some blurs here, okay? So the whole topic was energy consumption, reduction of energy consumption. And this is a perennial problem, has existed more than a decade ago, multiple decades ago, and continues to exist now. And so like one of the papers I had seen at that time was a paper by Powers in the IEEE proceedings, which was a really nice journal. I don't know if they still have it, but it had some really fantastic papers, including one of my own, Home RF, but that's the whole story, but that's a joke. Anyway, so that paper particularly said that energy power doubles every 35 years, and that's incredibly slow. Now, I haven't actually followed it to see what is happening since he wrote the paper. He wrote the paper in 95, and then he had, and all the work that was going on at the time was about optimizing components. So sort of I say, well, you could optimize the circuit designs, right? You could optimize radios, you could do dynamic power management, that was a thing, that was in vogue. You could also do redesign protocols to be much more energy efficient. So this was sort of like a whole set of things that people had. They had to, I have listed here some of the things that were going on. For example, it says build very efficient CMOS circuits. Okay, so we talked a little bit about that in my session with Teresa. There were lower the CPU frequencies. That was a well-known technique. People were using that. Smartly use the different power modes that came with all these .11 devices, and so on and so forth, right? So there was all these methods, but there was no approach in my mind that took a very systems level approach. By the way, these are the wrong set of slides, so that's okay, I guess. So there are things in there which I changed, so you might not see it, but I'll just pretend these are the right slides. So we had this device called the Compact iPack, okay? And I'm going to show you that device. I actually brought it with me. I'm going to show you what we built. But it was well before the iPhone, right? There were other companies doing great stuff with that. There were PDA. The battle was between the PDA and the phone. Was the phone going to become a smart? Was the cellular guy is going to make a smartphone, which becomes, or the PDA guy is going to make a cell phone? So that was sort of what was going on. And what this graph shows, I don't know if you can see it really well, was sort of the standby time. So what was obnoxious about these devices was that even if you were not doing something, the battery would slowly drain out and it'll die. Okay, so even if you did nothing with it, because you had to wonder what was going on underneath that was causing this to happen. And so the red line shows how, for example, I'm trying to read myself here. There was a Motorola phone that died, and you can and then what you see in the blue line is a line which had an iPack with a wireless card in it, the .11b at the time, which is 11 megabits. And then there's another line that you can't see, which is even further there, and that is when the power save mode. One is with the cam mode, which is always on. The other one is the power save mode. And what you can see is a tremendous difference in how long, the horizontal axis, if you can see it, is the number of hours that the device is lasting. So you can see just visually how much difference there was between a cell phone and a PDA, right? And with that kind of difference, it was just not going to work out. Okay. So we took a very system-level approach at the time, which was sort of radically different than the component-level approach that many researchers were doing at the time. So we looked at it very holistically, and then the idea was, can we just now reduce the power and bring it close to what the cell phone does? Now, so what was the problem? The problem was that the wireless card and the device had to be on to get calls. So if you were doing a VoIP call, if my device was not on, I'm not going to get the call, right? But the problem was when you keep it on, then you were draining the battery. Okay, that was the big problem. So you just think like a system, and you say, why can't I build a system which can be off all the time, but somehow magically wake up when the call shows up, right? And so I really do apologize for these bad slides here, or I'm not sure what the thing is, but so I'm actually literally. So anyway, so then the proposal was that let's take a small radio or low power radio, put a processor next to it, and then put everything to basically make it dead, but keep that part alive. Okay, so I'll keep the processor and the Wi-Fi and the RF chip alive, and everything else dead. And so then the thing was that, well, so now if the call came in, you will trigger the iPack and the Wi-Fi, and will turn them on when the call arrives. And so that way you will not be wasting, the iPack will not be wasting much energy. So that next question was, okay, this is all fine and good. We had to prove it. So prove it, you have to build it. In Microsoft they say code is king, but in this particular, in research, the philosophy I've always followed is you got to build the damn thing before I'm going to believe you at all. So we built it. Okay, so a little bit about the system implementation. And again, the reason I'm going through this is because it was quite radical at that stage of our progression in terms of how systems were, how the research was progressing along. Remember, MobiSys had not been created. MobiSys was created in 2003, so this was in MobiCom, and a lot of papers had to do with simulation, a lot of papers had to do with NS2, if you remember that. And there were very few papers that were actually doing the very heavy system work. So we picked this radio. There's some data here. You probably can't see it, but it was an RFM TR1000 chipset. It tells you here in the slide, how much voltage it was, what sort of modulation it used. It was very simple modulation, amplitude shift gain, and then the numbers that, in terms of power numbers of that chip versus the radio. And you don't see it, but they're very, very different. It's very, very low. Okay. In this picture, what we're showing is this was, and as I look back, I've been very sort of proud of what we ended up doing. What you're not able to see very well because of the slide is these black boxes are all different kinds of sensors. So when we decided to build it, it occurred to us that we wanted to build a research prototype, so we wanted to actually put lots of sensors in it. So touch sensors was there, accelerometer was there, and a bunch of others, capacitive sensors were there. So this is again before iPad or iPhone, and this is before any of these PDAs ever had any of these sensors, all right? So we had instinctively knew that these kind of sensors are going to become very important. Then we build the hardware. So what you see here is on the rightmost is that iPack, and on top of it we have what we called Smart Brick. Okay, and then that's his name, and then we have a mini brick. And this hardware, this shows the hardware. You can sort of see the coin and the size of that hardware, and you can see it has all these different sensors that are in the particular hardware as well, and how it looks. And I have preserved that hardware for the last 16 years for just this time. So here it is. I have 2 of these devices. So this is the exact same hardware that we actually built, and it works. Well, I had a hard time with the TSA this time, but this actually does not look very kosher. Anyway, so I have the hardware. You should take a look at it. It's really cute. And besides the hardware, the next question for us was to build the software. And so the way, because this slide is not working, I'm going to tell you the way it worked was that you had to have a server in the air, and the server would actually have running the SIP protocol. If you remember, the SIP protocol was this telephony IP PBX protocol. And in addition to the SIP protocol, it was running our protocol as well. And so what would happen is the device would come in and register with this server and say, hey, I'm here, and that would be just anything. And then it would also register with another server or a PC that was in close proximity, which had this little smart brick that I said. There were 2 components, smart brick and mini brick. Now, when Bob or Jason wanted to call me, and my device was sleeping, he would call me, and the server would pick that call up and then send it to the closest server the closest server to me. And then that server would then use this little device, send me a ping message. My device would then immediately get up, wake up my bigger PDA, and wake up my radio and Wi-Fi, and then connect with Jason. And that's how it worked. And we built the whole thing. As you saw, we built the hardware, we built the software. This is the call back and forth that went through. This is sort of the protocol that we followed, and we built it all. Okay, the other interesting thing that we did in this paper was measurement. Okay, this is, again, like I was saying, I'm taking you back to 2002, where these things were a little bit different than the way research was progressing. So in the measurement case, we sort of came up with this way of measuring power. And what you don't see, what you probably can't see very well, is essentially we measured the current going through it. We had laptops here, and we put in a current meter and pushed the voltage through it, pushed the signals through it, and then measured the current as it was being used for each of these devices. Now, this thing has also stood the test of time. Many thousands of papers that have been written after that have actually used similar thing. The interesting thing here for you to just pick up here is how power save mode works. You can see there's an idle power in the back. So in the baseline is the idle power, and the blips are when it gets up and asks the access point, hey, do I have any packets to give? And then goes back to idle power. The problem was the idle power. Why is it even there? Like it should be just shut down. And what we designed was something that shut it down. Okay. So this is the picture I showed you in the past. So what did we get? We got this line that you see, the new line. So let me just show you this. And then this line that you have is the line that we had as an upper bound. That is when we didn't have any wireless and just the iPack was sitting, because we couldn't really do much with the iPack. But then when then you see a green line, and by the way, being farther is good, because that's the thing. Because remember, the horizontal axis is the number of hours that the device is awake. So you can see there was 115% improvement over what regular systems can do, and the latency was very minimal. So the system actually worked really well and saved you much more power than any of the pieces of work that was going on at the time, which was to work on the different components of the system, right? So, and effectively, if you think about energy saving, the only way that you really do energy saving is you just shut things off and don't do anything at that time. That's your best energy saving solution, and that's what we were trying to achieve. We also did some interesting other measurement. This is just graphs that you can't see, it's a blob, but what it says is, it's basically, we took, at that time, cell phone usage used to come with how many minutes you're using per call. So we took took these bills that we got from AT&T and mapped the number of minutes that you were using on your cell phone, and then used that to come up with these graphs here. And they basically show you what type of savings we got. So the blue line is what we got. The green and the red line is the past with some modification. And what really we got was that we were awake after 14 hours, right? So in the other cases, you were down after 8 hours or 10 hours, but we were fit 14 hours and we had a lot of battery left. And that was the key for us because we thought if this thing could last for 1 day, then I can charge it again and then do it. I just didn't want it to sort of break in the night. I'll just go through this. And then we did a lot of analysis. The paper is actually quite good. I reread it recently, just to sort of refresh myself. And I was impressed myself. So anyway. So what did we really accomplish? We sort of started off with this iPack, which was using 112 milliwatts of power even when it was off, okay? And then and that equated to about 35 hours. And then when the iPack had Wi-Fi on it, then and with power save mode, it was only awake till 14 hours. This is with nothing happening, like so no calls and everything else. But what we accomplished is that we got our iPack to work for 30 hours out of from 14, taking it from 14.5 hours to 30 hours, which is pretty close to the 35 hours boundary. And we got about 40% saving with sort of real users. So it was a significant step forward. All right, so I'm going to quickly end now, but what I want to say is that, so in this community, I know we care a lot about what we do in research and how does it actually impact the world. And the problem has always been, it is very hard to take something that happened here and trace a history and be able to say, claim victory, that this actually came out of research and the world has benefited from this. So when something like this happens, you get very happy. But I'll tell you the caveat with this. So from an impact perspective, what this thing is, this is a Google Scholar I just picked up in terms of the impact with the papers, how many papers have been citing this thing. But really, the commercial aspect, as Marco pointed out, was that in 2006, May 2006, the IEEE created a working group. It was called Wake Up Radio Working Group. And at that time, it didn't have a number, but now it has 802.11ba. And it says, and I'll read it for you, new capability for 802.11 to enable energy-efficient data operation without increasing latency. And then no dependency on the PHY. There should be no dependency on the .11 PHY, so basically it should be used by any .11 version that you have. And they have a picture here, and the picture is quite interesting here. So let me, I can walk, that's great. So the picture shows you got an AP, you've got a cell phone here, and then here is the radio, this is .11 radio, and then you have a low power radio, wake up radio, right here, okay? And then he says, when you do not have any received thing happening, nothing's going on. But when you receive a packet, this low power radio here sends a signal to then wake it up, and then you have it. So here you go. This is exactly what we did, right? There is no sort of ambiguity in the terms of what we did in 2002 and what they created a study group for in 2016. But they did not cite us. They did not say anything about us. It just didn't, if you read all the literature, it just says, IEEE breakthrough technology of wake-up wireless. I mean, that's fine, but this is what happens in research in terms of how you can actually trace things down. So you can, there are references here. And then there's a lot of marketing, actually, if you look at that stuff. This is an infographic that IEEE came up with, and if you read it, you will sort of see it's pretty similar to what we did. Actually, it's verbatim, looks like, from what we did. So that was great. If you do any of your search engines, like if you go to Bing, then you get a lot of this. If you get a Google, you probably might not get. That was a joke. Okay, so there's a lot of coverage on this stuff that's there. Now, this is my last slide, reflecting on it. I think that what I learned, or what we learned from this was that having multiple radios with different characteristics on the same device can be amazingly beneficial to both power, capacity, and functionality, and everything else. So one of the big things we did here was to separation of control and data. And so you hear SIGCOMM, for example, you think about software-defined networks, and really what the software-defined networks are about, control and data separation. Well, in the wireless community, we were doing this forever. Like, we were doing it a long, long time before this notion of separating the control and data came into existence, and this is one example of that. But the other thing I wanted to say is that over a period of time, we came up with these 3 principles of how you want to do this separation. So there's this principle of separation, there's a principle of diversity, and then there's a principle of flexibility. And what they talk towards is that the first principle of separation is the control in data, separating the control in data. The second is about diversity, means when you have different characteristics for the control channel and the data channel, that is actually helpful in many meaningful ways, because, and you can go deep into it. And then the flexibility is, hey, you got to make a lot of the stuff is programmable to do it. And so we wrote a bunch of papers to show this, but then I moved on. And but really happy that this happened, and I'm really thankful to the committee who selected this paper and saw there was merit in the work we did. So my deep thank you for that. And I'd also like to acknowledge Mike. Mike, why don't you come up? Who is come on up. Who, without whom none of this would have happened. Eugene is not here. Eugene was my student at the time, and he built it, but he couldn't have built it without Mike. Mike actually manages the hardware group, hardware research in Microsoft Research, and so he helped Eugene build these things and just made everything possible. Otherwise, it would just be a concept in our head. So I do want to acknowledge you as well, Mike, for this great thing. Okay, I'm done.